Okay, I'm starting on the dot because this is going to be kind of a race to the finish line here. When I started off planning out this talk, I made the mistake of calling it optimizations and overheads. And the problem with that is I kind of failed to say what kind of optimizations. So me, being me, thought, hey, the best solution here is all of them. So consequently, we're going to be covering a fair bit tonight. For anyone that doesn't know me, my name's Chris Murphy. I handle evangelism for Unreal Engine within Australia, New Zealand, and Southeast Asia. Kind of drop in on different cities and run workshops, help different teams, etc., etc. For today, we're going to be covering quite a few topics, as I mentioned. So to begin with, we're going to be looking at art budgets, just generally what you've really got to consider when you're first forming them. Blueprint optimizations, network optimizations, graphical optimizations, and then a general overview on profiling and how to have actually an idea of what's going on within your project. Now, to begin with, we're going to start looking at this concept of planning your art budget. And again, I'm going to apologize. I will be speaking reasonably quickly today because some fool put 70 slides in this thing. So we're going to be starting by looking at planning your art budget and what's kind of entailed in actually kind of working out where to begin when it actually comes to optimization. Because what most people don't realize, / what we're all terrible at as game developers, is your optimization really needs to start pretty early in your project. And by that, I'm kind of talking not even day 0, like -1. First getting an idea of your project, start getting an idea of where things are going to go wrong. It's a pretty important thing because your projects inevitably, if you do your optimization at the end of a project, look, you're going to be able to clean things, you're going to be able to fix things, but the truth is that if the decisions you make at the start of the project are intelligently based on mechanisms that you're going to have for optimization, your job at the end of the project is just going to be way more straightforward because you did it right. So we're going to be covering a few things when we're talking about art budgets. There's going to be platforms, the expected development time, your art style, single player versus multiplayer is a pretty important one, character counts, and lighting models. Now, to begin with, we're going to look at this concept of your target platforms. Now, who here has released a game on console? Okay. Now, who here planned, with full intent on releasing on that console when they began development? Yeah, so half of you. Yeah, so what happens here is there's this real trick where you start developing and you go, oh yeah, this'll get released on PS4, or this will get released on the Xbox One or Switch or whatever else. But the truth is that when it comes to your hardware requirements and your hardware specifications, you really need to keep in mind from an early point what those limitations are potentially going to be, because there are some things that are just not going to work on certain target platforms. For instance, there are better ideas in the world than running planar reflections on mobile VR. It's just not going to happen. But as well as that, you've also got this thing where if you start developing a game now, realistically, you're probably going to be releasing it in a year, maybe 2 years' time, if we're being optimistic. And what usually happens here is your consoles, look, they're very powerful, and they're static hardware that you know what the baseline is on them, but at the same time they're also going to be a nice kind of lower baseline for performance where you have to run on this hardware and above, and it kind of gives you an idea of what your PC specifications can be accordingly, because you know that there are target platforms. And as well as that, one thing that I can't stress enough is that when it comes to developing for your target platform, try and have some bad computers in your office. It's really easy to be developing and have your sick 1080 machine running an i7 and something else in it that's going to make every other gamer cry. But what happens is you need kind of an old and busted machine in the office to actually test this stuff on, because it's so easy to just assume that something's fine, and then it turns out that, hey, if you're running on a DX11 machine instead of DX12, something's going to go wrong. Or, hey, it turns out this range of cards didn't have this optimization where everything runs smooth as silk now. So that can be a real trick. Now, the next thing I want to cover is art style. So picking this really early on actually has some pretty serious ramifications for your project. If you're going for realistic, such as the Boy and His Kite demo, you're going to have an incredibly high texture memory usage, because when you start really kind of relying on photogrammetry, you're just going to have huge textures. And when it comes to huge textures, they have accompanying huge file sizes. Now, when you look at something like Paragon or the Infiltrator demo, this is where you're going to start looking at what we call a hyper-realistic set. Now within this, we get around a lot of the detail issues by having things like detail textures that are kind of coming in. So you have slightly lower res textures for your main assets, and then you're running tiling textures over the top of them. That way, unlike something that was photogrammetry, where if I zoomed in on a person, I've got like each and every pore, in something like Paragon, we're going to be using a tiling pore texture that is masked in at a certain location that saves on memory overhead. Because the thing to remember when it comes to memory overhead for textures is really that, remember that every single time you double your resolution in textures, so you go from a 1024 to a 2048, you're actually adding 4 times the memory overhead of the previous texture type, because you're going twice in 2 directions. Does that make sense to everyone? So it can be quite painful. Then you've got other things like Fortnite. And so Fortnite is more of like a cartoony style. And look, that's going to be great for texture memory overhead, because very few things are going to have normal maps. And you're going to, it's all reasonably tightly controlled on the texture memory side of things. But one big problem you will have is you need to take into account your vertex shader pipeline, because all of a sudden, when you're doing something cartoony, you're going to have a lot more of that like vertex animation of things popping out and things kind of flexing and all of that old school animation technique that looks quite nice. Now the next thing I want to talk about is multiplayer versus single player optimization. This is a really big one because it can add some serious constraints to your project at a very early stage if you don't consider it. So picture this, all right? The top environment and the bottom environment. You have a sniper laying in the field, and on high graphics, they're laying in all of this beautiful concealing grass. And on low graphics, they're an idiot laying in the middle of flat ground that everyone can see. Now, the problem here is that at an early stage in development, you need to actually look at some of your art requirements and say, what is just going to have to be there whether I like it or not? Because one of the first things that you nuke when you're running on like low-end machines is you get rid of foliage, because it's just a whole lot of transparency. But if you're going to be running something that's going to be a game that's going to be competitive, where people are concealing from one another, you unfortunately need to just accept that when you're making your art budget, this is something that has to be there, and everything else has to be designed around it. Now, in addition to that, the other one of those big things that needs to be considered quite early is your lighting model. So you need to consider whether you're going to be having like full dynamic time of day, or whether something is going to be more statically lit. And they do have different issues there, but as far as computationally speaking goes, then running static lighting is a good move. However, you're adding a lot more light maps and everything else, so that does have memory costs associated with it because of that. One thing that I would recommend checking out though is with the release of 4.15 with Robo Recall, we brought in lighting scenarios. So if you do still want to have different times of day, you can actually bake out different lighting scenarios in Unreal and then just hot swap them. So you can they go into the house at daytime, they do a mission, they come out of the house, and now it's the statically baked nighttime. And it's cost effective while also still providing some variation to the player. Obviously, this doesn't work in all cases. If you really want them to be able to stand in a field and they're changing time of day, you're either going to have to use dynamic lights or some post-processing to hide the whole effect. The next thing is player counts. It's really easy when developing a game to say, oh yeah, look, we're going to target somewhere between 8 and 32 players, but we're really trying to figure out what's going to go there. Because there are some games that just really, really break down whenever you have high player counts for various reasons. One of the big things here is just, look, if you've got characters that are between 5,000, 20,000 polys, if you add an extra 15 of them that you hadn't really planned for, and some matches have them and some matches don't, you really kind of need to just expect the worst case scenario when it comes to designing your art budget and assume that inexplicably all 32 of them are probably going to end up on screen at the same time at some stage, and what's going to kind of come into account. Because when it comes to working out your art budgets and what you can and can't have, you really do need to account for pretty close to the worst case scenario. I mean, there are some contrived situations that you've just got to accept are going to run badly, but wherever possible, for things like player counts, just assume that they're going to try and form a human pyramid at some stage, and that's going to need to render. Now, all of these things kind of contribute to developing what's called a vertical slice. So a vertical slice is just the development of something that looks like a finished product, but it's actually about this much of your game. But it's enough that you can kind of get an idea of the performance in your scene, of what's going to happen and how it's going to go down. It's quite common for vertical slices to have a gameplay like elements attached, and I do recommend that if you've got the time and ability to do it, purely because the more explosions and things going on inside of your vertical slice, the better your representation of how this is going to perform for the rest of development is. So this all kind of comes into your art budget. Typically when it comes to your art budget, you're going to be kind of having a document that's being created that's going to have these kind of things in them. You're going to have your asset and scene poly counts, just your upper limits of what you expect to have at any stage. Bone counts for characters, you usually want to like limit that at a very early point and just say, look, we're clamping it at 75 or whatever it may be. Maximum texture sizes between asset types. So a hero asset is allowed to go up to 4096, but anything else is going to have to sit down here. Your draw call counts. Your post-processing standards are also very important. You don't want some mapper to go into just one map and enable bloom when it was turned off on all of the others. And that does happen because they're like, yeah, it just looks way better that way. And you're like, yeah, but now there's one map. It falls outside of the rest of our standards. And your target frame times. And target frame times are very important because, I mean, if you think of something like VR, your target frame time, you're trying to crank out 90 frames per second. More than that, actually, because you never want to dip below 90 FPS. Whereas your target frame times on console, you know, you're sitting down at 60. On PC, I mean, I'm not using the phrase 30 to 40 is acceptable, but it can be. So for the next section that we're going to go into, one thing I'd like to flag is generating console commands. There's a lot of console commands in Unreal, and a lot of them are kind of hard to find. One thing that you can do is, this GIF is going to restart in just a second, is you can click the help button in the top of your editor and scroll down to console commands, and it's going to generate, console variables, sorry, it's going to generate an HTML file with all of the console commands you can have in like a nice, searchable, easier to read than this GIF format. So I do kind of recommend kind of checking that out because it is really going to help out. Quite often if you're trying to fix something or optimize something, you're going to be like, well, where do I even begin? So opening that up, including search help, and then starting to type in the words of, I'm trying to fix draw calls. Now, next up we're going to be discussing blueprint optimizations. So this is just kind of going to go over some of the do's and don'ts when it comes to blueprint development. And like, before we begin, I do want to like really be clear that when it comes to your blueprint development, what happens is it's a fantastic tool, and people are going to be able to smash out weird and wonderful effects that you never intended or never even thought of having in your game because, you know, artists have all of this power to create now and it's exceptional, right? Except the problem is at the end of the day you are still talking about a lot of people that typically don't have straight computer science backgrounds. And because they don't have a straight computer science background, they're making their own tools and everything's looking good, but under the surface there are going to be slight problems that are starting to emerge. The typical things that you notice happening whenever you've got people that aren't really trained in programming using Blueprint are reliance on tick functionality, a misunderstanding of pure function execution, abuse of hard references, and overuse of expensive functions such as get all actors of class. And the thing that we typically recommend here is when it comes to development, you really want to make sure that you're, wherever possible, having some sort of kind of artist and engineer mentorship going on. So just having someone that your artists can fall back on and just ask questions of, and every now and then you've got your engineers kind of just looking over some of the stuff that the artists are doing to just make sure that it's being done in the right way. Because like, it's not that the artists are intending to do something that isn't performing well. It's just simply that quite often, if you don't know a technique even exists, you just don't implement it. And then when someone shows you that one time, you're like, I can bind to functions, and everything changes for you. So the first of those issues that I brought up was over-reliance on tick. Now, over-reliance on tick is a pretty common one. Essentially, for anyone that's unfamiliar with what tick is, essentially every frame, the game goes through and grabs every actor that can tick and runs its tick function, which is just basically the function that says, this is what I should be doing all the time. Now, the trick there is that the more actors you add to a scene, the more and more stuff you're going to be like crowding into tick. And one of the tricks there is that it's really easy for you to start smashing out blueprints. Like, let's say you're making some blueprintable trees, and you can punch in variables, and it's procedurally adding branches or something, and it'll be really cool, and it'll look great on screen. But if they haven't disabled tick on that actor is now ticking for no reason at all. You know, and conversely, you look at something like volumes, right? So if you want it so that when a player enters the volume, it's going to start doing some stuff, and then when they exit the volume, it's going to not do anything. Quite often what happens is people just put a branch coming off of tick, and they're like, if someone's in there, do things. But realistically, you might as well just disable tick until they enter. Then you actually call allow tick as a function in Blueprint. Start ticking. When someone exits the volume, you go, hey, is anyone still in there? No, let's disable tick again. Because just, here's the thing, is like ticks by themselves aren't expensive. But ticks when you have a game with like thousands of actors going on and all of your projectiles are ticking when they actually don't need to tick, you know, like these kind of things just, it adds up and it kind of just, it can end up being death by 1,000 cuts purely because all of your lights were blueprints and you didn't realize that they had extra functionality that was going on in the background. So when it comes to handling ticks, what I typically would recommend is at any stage you can type in dump ticks into your console and it's going to spit out this beautiful looking thing, which will tell you every actor that's currently ticking. So opening that up, quite often just scrolling through that will make you go, ah, yeah, that's not meant to be happening. And it's just, yeah, typically it's pretty obvious. And when I'm talking about that artist, engineer, mentorship kind of a deal, keep in mind, again, on this front, that this is a good thing for engineers to every now and then just look around the room, type it in, and be like, you, I need to talk to you. Because it just kind of raises red flags pretty early. The next thing I want to bring up is expensive functionality. So as far as expensive functionality is concerned, get all actors of class is a major culprit. So for anyone that's unfamiliar, get all actors of class just returns a list of every single actor of a certain type, which is great. Until you're running it every frame and your engineers are crying in the corner and you're like, what did I do? So that's it's a real issue because what I would recommend for get all actors of class is if you have to use it, consider just caching that somewhere and just really thinking to yourself, how often do I need to run this? And then doing the thing to get them crying in the corner. But no, actually like really kind of considering when it's necessary, when it's going to be essential, and what's going to be like a good time to do it. Spawning, most people don't realize how much overhead happens whenever you spawn an actor. Spawning's got quite a bit of overhead, and every component you spawn inside of an actor has its own additional layer of overhead. Who knows the concept of actor pooling? Okay, so there's a couple of you. I'll cover it. So basically the concept here is just that spawning's expensive, right? And if we're going to keep spawning things, we're going to add overhead. And it's going to cause hitches quite often because if you spawn 10 things at once, that single frame is now going to have all of that overhead. So consequently, there are two things here that work really well. One is pooling. So if you think about firing a machine gun, if they're going to be firing a whole heap of bullets and the bullets are actual projectiles instead of like instant traces or something, you might want to actually, instead of destroying the bullet when it hits the wall, you make it invisible and you disable collision and you store a reference to it inside of the person that's firing the gun. And what happens is instead of spawning a new bullet, it just grabs an existing bullet that's stored in its array and shifts it back to its original position and just reuses the same thing. And you can run some timers on there to just clear out these pools every now and then. But it's kind of a nice technique to really kind of save some overhead. The other little thing that you can do on spawn is if you're going to do a bunch of spawns at once, just distributing them over a half a second and just spreading them across a couple of ticks isn't the worst idea, just so that you're not doing all of it at once and causing a hitch. And the final thing is just loops. If you're doing loops and you're going to have loops inside of loops, you really want to consider just using loops with breaks. Every now and then, if you're going to be iterating through an array a lot, sometimes it's just a good idea to every now and then run something through the array that sorts it from like highest to lowest cost or something. And then when you do have to iterate through the array, just bail out early because you're no longer going through every result looking for the highest. You now know that the second you get something that's up here, like this end of the array, it's good for us. And if it's at this end of the array, it's a different type of value. So every now and then just running a sort function and just keeping things clean. You're adding a little bit of overhead here, but you're probably saving other things here. The next thing is hard references in Blueprint. So most people don't realize it, but every time a Blueprint actor, who has used casts in a Blueprint before? Okay, that actually shows me how many people have used Blueprint. So when you're using a cast in Blueprint, you're getting an actor and you're saying to it, is it this type of thing? So if a volume says whenever an actor enters it, do something, the volume might cast to a player to see if it should do a thing on players, right? Now, the trick here is that if a volume references a player, even if the player is not in the game, it's going to actually load the player blueprint into memory. And what it's then going to do is, because it loads in the player blueprint, it's then going to load every single hard reference to a cast that's inside of the player, which is then going to load more stuff. I'm kind of climbing an invisible ladder here, but you can see what's happening, is we end up accidentally, if you have overuse of casts, you end up accidentally just rolling 90% of your game into memory because you happen to have just things that were referencing things statically. And it's a good time to use interfaces instead. So an interface is basically just a way of saying this actor has these function calls. So you check to see if it has an interface instead of it might be a pickup interface. And then from then on, the actor doesn't need to care what kind of actor it is. It just cares that it has the interface. And this can kind of kill that from being a problem. Because, look, the memory usage there isn't always the worst, but what it is a problem for is load times. Just because you're loading in all of these blueprints, it'll load one thing which accidentally just loads in a full chain of things, and it just extends your load times. Next up is pure versus impure usage. This is one of those things that it's very easy to not realize how some of these things are going on. Just whenever you run an impure function, like the one on the left, it's going to run it when the execution pins are hit. You know what I mean? So when something goes into that arrow on the left, it runs the function, and the result from it is going to be stored at that exact time. Okay? Pure, on the other hand, doesn't quite work like that. It'll get called when it's referenced, but it also means that depending on the function type, you're going to be recalling certain things. And quite often, you actually only want to call your pure functions once. You know, you actually wanted it to be called and cached. You didn't want to just keep running these things. And it's very easy to fall into that trap. So just remember to use local variables to just cache things if you want. There's another really dirty little trick where you can actually use macros to cache variables because they can create their own local variables inside of them. So if you want, you can just roll things up in a nice little macro that'll just put things in there. But yeah, as I said, just be aware that quite often you'll have a huge pure function chain that you're calling 3 times, but you really only needed to call once and just keep your data. So other general blueprint optimizations that are worth noting, obviously there is just the first one, which is, look, C++ is quicker. Yes, blueprint can cook down to C++. It's not quite as fast. It's pretty close, but it's not quite as fast. At the end of the day, the structure that I would typically recommend for most of your key features is, so you get your engine class, like actor, and then deriving from that, you're going to have your native base class. So that'll be like the C++ level base. And then you have a blueprint base class, and then from your blueprint base class you then have your child. That way you can just push things back up the pipeline into C++ wherever it's necessary. Like if something's going to be very expensive, just throw it into C++. Like if it has to happen, so be it. And then your blueprint functions, your blueprint classes beneath it can then reference the C++ calls. Next thing we're going to cover is network optimizations. The general rule of network optimizations is that you're doing too much too often. And like the golden rule is really just replicate as little as you can, as seldom as reasonably possible. A really useful command here is just net dot, and then there's a ton of different commands that you can use here. It's worth noting that 4.19 is bringing in a lot of the engine upgrades that came from developing Fortnite. So for anyone that's unfamiliar with Fortnite, it's got a 100-player battle royale mode. And because we needed to support 100 players over a really large map, we fixed the engine up to do that. So you all get that. The trick to that is that, yeah, there's a lot of functions coming in, so just be aware of that. The net dumple relevant actors shows you what's currently replicating, so that's a good heads up to just get an idea of what's replicating, and you can look at it and say, do you actually need to be replicating, or has someone checked that one box because they wanted an effect playing one time? One of the new things that's coming in for 4.19 is network relevancy view mode. So this is quite nice. Essentially, you can specify actors to have, at a certain distance, they stop replicating until they become relevant again. So kind of having this view mode as well also lets you see which things are flagged as always having to be relevant and which things are just waiting to become relevant before they kind of pick up a channel and start replicating. Just generally, if you're looking here, you can see that yeah, anything orange is kind of a candidate for dormancy, but it's still going to be using CPU cycles to see whether it should be entering a dormant state. This is the ugliest slide in this presentation, which is the big list of things that are coming in 4.19. This is more explicitly covered in a blog post that went up recently on Unreal Engine's blog. The big ones here that are worth noting, there's a bunch of little things like no longer pinging everyone unless you want to. Two bigger things like the ability system in Unreal is now it significantly better accounts for relevancy, so it's no longer going to look at doing extra things to like replicate information for a battle that's happening kilometers away from you, because you don't need that information if you're a client. So the next thing we're going to be looking at is graphical optimizations. And this is one of those things that, as I said, your game looks good, but you've really got to make sure it's going to be running on as many machines as possible. And the first problem there is really just like the calls. You really want to make sure that you're, as often as possible, kind of limiting your draw calls and kind of cutting back. For anyone that's unfamiliar with it, every single time you have a material being rendered, you're going to be doing another draw call to do it. And certain material types are going to have their own other issues because if it's transparent or whatever else, it's going to be doing additional calls that are stacked on top of one another. So wherever possible, you want to try and cut back on this. And there's a few different ways that you can do it. One of the systems that we've brought in is hierarchical LOD system. So this has been floating around for a while. I think I have it written there, 4.11. Essentially, you can get a big old volume, drop it around something, and just say make LOD. And what it's going to do is it grabs all of the actors that are encased in that and produces a single mesh and a single texture for them that is what you see at a distance. And then as you get closer to the actor, it swaps out the LODed version, the HLOD version with the actual version. This is what we use in Fortnite for when you like dive out of a plane at the very start. Well, not a plane, out of a floating bus. It's just weirder to say floating bus. So you dive out of that at the very start and you can see the whole map. And the reason you can see the whole map is because it's actually just like HLODs of the whole map. You know, like at a distance we're just doing way fewer draw calls, and it's not until you get close that we kind of put in the prettier versions of these things. And you can see how it kind of works in different areas here. And wherever possible, you know, you can batch materials together and kind of save. And this uses Simplygon by default, and it falls back if you're not using Simplygon in your build into the actor merge tool. So the actor merge tool can be used by itself as well. It's just a really simple little tab that you can enable. It's in your developer tools. And all you do with this is you can just select a bunch of actors and click the merge button, and they're all now going to be together as a single model. So if you're going to have a whole heap of situations where these things are always going to be appearing in the same setup, in the same way, at the same time, well, you might as well just merge them down and share the materials across all of them. Because that way, if like in this scene you've got the chairs are going to be now just in a single call for their material, so that's fine. The table's got its own material, but you've still dropped it back again from where it was. It's just little amounts that can get saved over time. The other really useful thing here is instant static meshes. So instant static meshes, there's Jack shaking his head in the front row. Instant static meshes are very, very useful. Essentially what you're doing is you're batch rendering all of these meshes at the same time. So what you're doing is you create a mesh and then you're creating an instance of it. And every instance has a different transform. And the other variable that can change by default is you can use what's called a per instance random inside of your material. So a per instance random is just a random float value that you can use for randomizing the color of every instance, randomizing the, it might be the scale, it might be whatever else. But essentially what you're looking at here is every single one of those cubes, despite being individual meshes, are being rendered in a single call because they're all just getting batch rendered at once. So being able to just kind of do that has some real benefits. One thing that's worth noting here is that you can't just add instant static meshes. You need to create either a C++ or a blueprint actor that is going to then know how to, like where to put each instance and how they're going to go down. So, but this has like a huge benefit. So like the foliage systems, for instance, is all being batch rendered. These things are really good for like, if you wanted to have a planet with a ton of asteroids around the belt that were 3D objects, like Saturn, that's the planet I'm thinking of. You don't want to render all of those asteroids, right? Because there's too many of them. But you can theoretically render them all in like a single batch call, and if they're pretty low poly and at a distance you're using different LODs for them, it can work quite well. And it's worth noting that we have our hierarchical instance static meshes, which is a different type again, and they're just a variant that has their own occlusion checks and visibility checks, so those are quite nice. But the simplest one to begin with is just instance static meshes and just see how they work. To add one, it's literally just, after adding a component, you're literally just calling add instance in Blueprint and telling it where and how big and what rotation it's got. So the next thing I want to flag is vertex counts. When it comes to your vertex counts, the number of vertices in the model is obviously always going to add overhead, but be aware that every single UV set that you add to your model, every one of those seams has to split along the vertice, and it actually adds verts to your model. So if you're adding a bunch of unnecessary UV sets, you're adding a bunch of unnecessary vertices to your model. It's just one of those little things that no one ever checks because the asset looks right, so we're good. But if there's additional UV sets that are cut up in different ways, you just don't realize that that's going on in the background. So every now and then doing a bit of a content audit and just checking your meshes to see if they're, like on import, someone accidentally generated additional UV sets that weren't necessary or things like that, it's worth checking in. The next thing we're going to look at is just general LODs. So LODs are a system that's just built into Unreal that you can have your level of detail. So you can drop from like a high to a medium, to a low, to an even lower. And we can drop through these and we're going to cut back vertices along the way, right? One thing that's worth noting that's a little hard to see is, so see you got LOD groups here, LOD settings. You can use that for auto computing LODs. So you can actually set up rule sets to say that every single architectural mesh has these LODs for LOD 1, LOD 2, LOD 3. Every single environmental mesh has these rule sets for LOD 1, LOD 2, LOD 3, and you just add the asset to the correct group and it'll auto-generate LODs for you that are the cut-down versions of them, which just saves a whole lot of overhead. And because typically you have these general rules that are being applied across the board anyway, you might as well just set up some solid groups and then just push things between them. Next up is material counts. As I mentioned, every material that is in there is going to be an additional call. So you might want to consider just using texture masks instead. So you'll say that wherever it's red, we'll be using this material layer, and wherever it's not, we're using this material layer. This was something that came in, I can't remember the exact version. I think it was like 4.14, may have been earlier. Basically, inside of the material graph editor for Unreal now, you can actually pass around materials themselves as a data type. You can make material layers. Actually, wait, maybe material layers are way older than that. Yeah, they are. Anyway, material layers can be passing around as a data type, and because they're passing around as a data type, you can then easily just set up what wood looks like, set up what tin, steel, back on wood, plastic, and say, you know, this comes into here, this comes into here, and this comes into here, and just render them all in a single pass instead of having to care about doing it in separate layers with separate calls, which is quite a nice solution. This is what we use in a lot of our characters for games like Paragon. It actually just uses masks to say this part's going to be carbon fiber, this part's going to be plastic, instead of having separate calls across the entire character in different regions. Next up is LIGHTMAP resolutions. So this is a really easy one to kind of mess up. Essentially, whenever you're generating an asset that's going to have baked lighting on it, it requires a UV set that's kind of an unwound version. And then all of the lighting is baked onto that with a texture of a given file size, sorry, a given resolution. Now what happens here is it's quite common for people to go, yeah, I'm just going to churn this up to like 1024 or 2048 because I want to get like a really crisp shadow, at which point anyone on your team that does optimization is back in the corner because it's just, it really kills performance quite quickly. There's an easy way to find this. You can go the developer menu and then just go down to statistics, and whenever you go to statistics you can actually arrange by LIGHTMAP memory usage, and very quickly you'll be like, who added this? And you can play the blame game. But definitely easy to pick out. So keeping them low is pretty important. What I would typically recommend wherever possible is actually using cascading shadow maps at close range. So whenever something's close to you, you actually do a dynamic shadow that looks quite nice. And then when it's far away, that's when you can fall back to lower resolution shadows because they never have to be that high res because they're only ever seen from like 30 meters away. Another thing that we have is distance field shadows, which are, again, another thing that can really kind of cut back on overhead. Those were brought in for, they're pretty recent too. We use them in Fortnite for distance shadowing. Just general lighting tips are, again, baked lighting is significantly cheaper than dynamic lighting and stationary lighting. Dynamic lights are expensive, but cheaper in deferred than forward rendering. I'll cover that a bit more in just a bit. Wherever possible, if you've got a small unshadowed light, it's basically like the pinnacle of light optimization. I already mentioned mesh distance fields a second ago, and also the other thing is that just because an effect was in a demo piece that we released doesn't mean you should use it in every single effect that you put in your game that's similar. It's really common for us to do a couple of like showcase effects inside of those things and be like, this is pretty. But if you look at the instruction count, every now and then they'll be quite high. Lit translucency is a real culprit here. You know the effects demo, the cave effects demo? That's got some really cool stuff in it, but there are sometimes things. So you really want to make sure that you're not kind of having fully lit steam on every single thing inside the scene, otherwise it's just going to get out of hand real quick. Just general tips as far as lighting are concerned. Minimize the number of dynamic lights that you have. Wherever possible, just disable shadows on them if you don't need them. Minimize the actual radius of them, so the more you can kind of shrink them down, the better. The dynamic shadow casting lights are the most expensive in UE, so if you can kind of cut back on that, you should. Watch out for stationary light overlaps, because if you have too many stationary lights overlapping one another, they fall back to being a dynamic light instead of a stationary light, which is, again, the most expensive type. Also keep in mind that if your skylight is stationary, I believe that counts as one of your stationary light overlaps, so if you do that, you have fewer lights to kind of tinker with. Cull shadows as early as possible for any given asset. If they're not going to see the shadow when it's from me to the door away, then it doesn't need a shadow. You know, just nuke it. You're still going to need it on your big objects, but your little things probably don't require it anymore. Finally, for lighting, consider using IES profiles instead of light functions. IES profiles are just a physical rendering of how a light actually pushes out light into the world. We use this for architectural visualization and stuff like that to kind of get like nice effects along the wall. We don't have a single light here that actually is going to demonstrate that well, unfortunately. But they're used in the architectural demo if you would like to see how they function. But they do have more overhead than a regular light, but they have less overhead than a light function. Like we still do use light functions for things like a cloud pass overhead that's projecting onto the world, like little soft cloud shadows. But wherever possible, try not to. That's usually the main one that gets used for. As far as asset overheads, the other big one is just texture packing. If you've got textures that are being stored as grayscale maps, you may want to consider just packing them into the red channel being one texture, green channel having another texture, blue channel having another, alpha having another, and just where possible kind of crunching these down. This also lowers the number of samplers that you're having within a material, because if they're all going to be used on the same asset all the time, you shouldn't have 4 separate textures. Just where possible you want to kind of cut that back. Do recommend. Another thing that I want to kind of flag here is asset reuse. Wherever possible, look for excuses that you can design an asset that it can be used in multiple ways. A good example is that if you look at an asset like this, it's a little hard to see those lines, but if you look at an asset like this, see how it's got kind of that like rough bumpy section of one side of it? There's no reason that the other side of it couldn't be like a smooth flat surface, and that same asset can now be rotated and twisted and used for like a number of different ways. Like if I had $1 for every time I used rock textures inside of an asset that weren't meant to be rocks, I'd have like a lot of money. Yeah, so keep in mind that asset reuse wherever possible is just generally favorable. And just if you can keep that in mind in your initial design, your level designers are just going to have a much easier time as well, because they're really quickly going to start flipping things around and propping stuff up and doing whatever, and things are just going to come together much more quickly. Overdraw is the worst. So overdraw is basically whenever you're rendering something, just because it's translucent in the shader, it doesn't mean that you're not rendering anything there. You're actually still rendering the whole thing and then everything behind it. It's actually more expensive than just not having something there. So because most of the time transparency is more expensive than having a couple of extra vertices, what I would actually recommend doing is for things like grass. So if you look at the kite demo, the Aboyani's kite demo that we have, the grass is cut almost around the blades themselves, such that we're rendering more verts, yes, but there's no transparency overlapping wherever possible whenever you've got multiple blades of grass in front of one another. Because quite often what happens is if people want short grass, they end up having this much of their UV layer is the grass texture, and this much is actually just open blank space. And what they don't realize is all of this open blank space at the top on all of the grass as you're looking forward is overlapping each other and just causing a tremendous amount of overhead, okay? So kind of spending a couple of extra vertices to just cut around those things isn't a bad idea. And we actually built in a system like that for the particle systems called the particle cutout property. So if you have like a sub-UV being used on a particle, you can just load the texture in for the sub-UV and it does this, whereby it actually generates meshes that are as tightly cut around the shape as possible, which is really, really useful because it just keeps your particles from having that much overhead by just cutting the shapes down to their purest form. Really, really useful technique that honestly it was kind of a small thing when it was first launched, so a lot of people just didn't really realize that it's a feature in the engine, and we have a lot of features like this that are just like a single line hidden away inside of one of the editors. So it's a really useful one, definitely keep in mind. The next thing I want to bring up is level streaming. So when you're playing a game, you can stream content in and stream content out. So this is used in a lot of different projects, sometimes in very sneaky ways. My personal favorite that I've ever seen in this is, who's played Arkham Asylum? So you know when you're like walking up to the doors and the lasers are scanning you? It's because it's totally loading in the next level. That's why on fast machines they have really efficient lasers. They scan you, the door opens, you walk through, the level streams out. And this just kind of keeps the amount of stuff that's sitting around in memory just as small as possible, which is great. The other thing that you can do with level streaming that's really useful is you can use it as a layering system. This is what happens in Paragon. So you've got your levels set up such that you stack all of them on top of one another. And what you do is in your base level is the persistent map. Then you have the lighting map, base geometry, collision, foliage, and gameplay elements are they're all in separate maps themselves. The reason for this is you can now have someone do slight tinkering of like collision volumes while someone else is actively changing the foliage in the map. And you can have someone else who's just changing where the spawns are and how things are laid out inside the map and tinkering little details that way without interfering with everything else. Do you get what I mean? So by doing this, you can kind of have different people working on the environment at the same time without butting heads, because that's bad. A follow-up system from that that's worth noting is the world composition system. So if you're ever doing a very big environment, it's worth noting that the world composition system is in there, which is used for just automatically breaking the environment into tiles and then allowing people to kind of move between them and streaming content out and streaming content in. It's a pretty useful system. Now, we've discussed kind of world streaming. The other thing that's worth noting is the asset management framework. So this came in 4.16. Essentially what happens is you can now asynchronously load assets in background by just accessing, there's like a single asset registry class that you can just access and then just do calls on. So this is really useful for if you want to try and avoid hard references to things. But let's say you've got a quest coming up, right? And when the quest is coming up, if you know they're about to do the quest, in background you can now start loading in that information and the assets that are going to be required for it, so that when the quest launches in, it's not instantaneously trying to load those things. There's no hitch. It's just like, hey, we got those assets for you, and everything is fine. So the asset management framework came in 4.16. I think it was 4.17 that added blueprint support to it though. And this is used in the background of a lot of different things. Fortnite uses it pretty heavily, I think, for the inventory stuff. So just having all of those different items and how they're going to be, like whether they should exist in memory yet or not. Now, another thing that is pretty high up for optimization requirements are physics. So it's really common that you want to blow up a lot of things at once, but you can't because there's a lot of things. A mode that was added for Robo Recall was the immediate physics mode. So this is really great because what it does is it does the physics simulation only against static geometry. But when you're blowing up that many things, no one notices that they're not hitting each other. Because they're still hitting the ground and flying up and looking ridiculous. So having that there is quite useful. Next thing I want to kind of touch on here is the forward renderer. So it was brought in for VR, and it is excellent for cutting back overhead on VR. But it's worth noting that if your game doesn't really need screen space effects, if it doesn't really need screen space effects and it doesn't have many lights in the scene, like many dynamic lights, quite often running the forward renderer is actually going to save you like save quite a bit of overhead instead of using deferred. So this is especially the case in anyone that's doing like 2D and side-scroller games and stuff like that. Quite often I'm seeing some pretty significant performance boosts out of the forward renderer, even though it's not like a VR title. General do's and don'ts as far as pixel shader is concerned. Just don't do too much math. Don't use too many textures if you can avoid it. Don't use too many procedural functions because typically they're looping around. Noise functions are best rendered out to a texture wherever possible. Try to avoid using too many material layers if you can avoid it. And keep in mind that an if statement is still calculating both sides of the if. Even if you're telling it, even though only one of them is coming through, it's still calculating both. On the do's list is use textures for lookups instead of raw math if you can do it. Compress grayscale maps into single textures, as I mentioned. Minimize layer usage and use switch parameters to just turn off the functionality of things that you don't need. Now, profiling. So I'm going to be moving quick because I'm running out of time. But when it comes to profiling, essentially this is the concept of just working out what's going wrong in your game as far as performance is concerned. Basically, there are a couple of different ways you can go about profiling, but the underlying systems are, if you want to profile the CPU stuff, you can use the console commands stat start file and stat stop file, and what that's going to do is actually start recording until you type in stat stop file everything that's going on and tell you how much time it took to run those things. Okay? So this is a really nice way because you can then scrub through it in the Unreal front end and say, oh, hey, that shouldn't have taken 3 milliseconds. What happened there? And it gives you like an informed source to go from to actually start working out where your problems are. Now the other tool that you typically have is Profile GPU. So you can hit Control-Shift, and that's just going to break down everything you can currently see, and you can select any of those bars and see what was taking up the most time in your scene. So that's going to really kind of cut back on overheads. Again, my apologies for moving through this quite quick. So when it comes to profiling, there's a couple of just general best practices. Profile early and profile often, because you really want to stay on top of any things that are going to be popping up as issues. Test on the target hardware as soon as you possibly can. Make sure every team member is actually aware of how to profile. It's better for them to kind of be responsible for their own features coming in so that they know that they should be doing it right and they can test whether it's going to be having overhead. You want to create as little noise as possible, so I typically recommend disabling VSync and disabling frame smoothing, just wherever possible, just cut back on noise. If you can do your profiling inside of a standalone version of the editor, sorry, standalone version of the game instead of the editor, it's going to get rid of all the noise from the editor, so it's useful again. If you can do it inside of a proper build instead of a development build, that's even better again because that still adds overhead. Another really useful command that we have here is stat dump hitches and t hitch threshold. This lets you set timers that says that if anything takes longer than this amount of time to run, print to the log that took too long. So that's called a hitch, and that'll say that, hey, this frame took too long, and that can start helping you diagnose what's going on. Now, as far as the stat unit breakdown goes, so the console command is stat unit. The frame time refers to the total time for each frame. Game is your C++ or Blueprint operations. Your draw time is your CPU render time, and your GPU is your GPU render time. Now, your general profiling procedure whenever you're moving through this stuff is work out where the bottleneck is, what can go wrong in that scope, solve the issue, work out where your next bottleneck is, what can go wrong in that scope, solve the issue. And it's worth noting that for this kind of operation, you're really going to be coming across different things at different times because this will be a bottleneck disguising other issues, which will be a bottleneck disguising other issues. So when you want to start doing that, what I would typically recommend doing is looking at stat FPS, stat unit, stat scene rendering, and stat RHI. I'll be giving out notes on this afterwards, by the way, so don't get scared about me skipping through this so quickly. But essentially, stat scene rendering is the best source of early information on draw calls, and stat RHI is great for just getting overall information on texture memory usage and tries being drawn. Now, another tool that we have for kind of sorting this stuff out are the view modes. So we're all typically used to seeing things in lit mode, but it's worth noting that you can flick over to the shader complexity mode, which is going to give you an idea of how much all of your overhead is going in per pixel. The other really useful part of this is you can see your overdraw. So right here you can see that those transparent steam objects in the back are all overlaying one another and causing some serious overhead per pixel there. Quad overdraw is a new one that we've brought in since 4.15. Basically what happens is whenever you go to render a vertex while using MSAA, you actually have to render the pixel up, you render the 4 pixels around the vertex as a quad. And that means that if you have a ton of quads in one place, it actually adds quite a bit of overhead. So like wherever possible, kind of cutting out dense groups of quads. And this kind of lets you see what's going on in that way. LIGHTMAP density is good for diagnosing that issue I mentioned before, which was the issue of having really high texture resolutions. This lets you just see everything from like kind of a holistic view and be like, okay, clearly those pipes are being allocated way too much memory for light maps. Now in 4.15, we brought in a texture streaming method, which was cut back a lot of overhead and was quite a powerful tool. This is something that just kind of operates in the background, but it's worth noting that there's a ton of optimization view modes that go with it in identifying whether textures are too big or too small for a relevant scene. I'm just going to actually skip through these so I can get to the last part. These are just the different optimizations. The main one that you really need to know is this last one, which is the required texture resolution. So this actually looks for the worst culprit in every material and says whether the currently rendered texture on screen is too high a MIP or too low a MIP. So this tells you if the textures are actually just too high a resolution and you didn't need it to be a 4096, or it tells you if the other way around, whereby you're MIPPing out too early and you need more MIPs stored for the lower texture resolution. 2 more slides and then I'll bail out. Sorry, man. All right, so automation is the next thing I want to look at, which is just you can set up automation within Unreal for your profiling. So a common technique here is you set up a sequencer event, so a single track that runs through your map with a bunch of effects playing, and just overnight set your server or a machine to kind of just run that every night and profile it and just tell you the average frame time as you went through and identify where the hitches were. And because you're playing the same sequencer event every night, the same timings are all going to line up with one another, and you can see that, this area is a problem now. What happened in the last week that is causing that? You know, this is an issue now. Once your gameplay is basically complete, Unreal's got a nice built-in replay system that you can use to actually replay entire games that happened within the game. And you can use that and potentially use that system as well for profiling. So you start actually just running replays of the game through your profiling to see where the effects are and what's causing a problem. And that gives you a kind of a better overview on everything. Now, last slide is quite simply, pixels aren't always the problem. When you're trying to diagnose what's going wrong with your scene, it's worth noting that one of the best ways to figure out if something's going wrong in your pixel shader or your vertex shader is if you type in r.screen%, you can actually tell the screen to just run 10% of the pixels and just shrink it all down, right? And here's the thing, if your frame time doesn't change when you drop it down to 10%, that tells you that it's something to do with the vertex operations, like the world position offsets or the draw calls or any other number of things that's causing the problem. Does that make sense to everyone? So kind of like crunching down your screen and like ruling that out is a really, really efficient way of just working out what's going wrong within your project. I'll do my best to try and get these slides out to the public. My apologies for having to go through this so quickly. But we are currently out of time. So not questions. So thank you very much.